And right, so আজকে transformers করব, which is actually part of the AC topic, but I'll start here because it's connected. Right, so before I start the transformer, do you have any questions from induction? Last class we went through these different examples, right? Lenz's law. So কোনো question থাকলে আমাকে বলতে পারো regarding Lenz's law. Does anyone have exams coming up? Oh yeah, sure. দেখাচ্ছি যদি exam থাকে তাহলে I'll do a recap today, like questions and stuff very quickly. So তোমাদের exam date কি বলতে পারবো? একজন তো হয়ে গেছে তোমাদের mastermind এর শেষটা। আমার এখানে লেখা ছিল for November 3rd. Day after tomorrow. No, exam 3rd December. Not sure. Okay, let's go through this. You want to know what eddy current is, right? So eddy current, let me explain what this is. So the idea of eddy current, the definition is this. It's unwanted current induced in systems that can lead to energy loss of the system. That's what the definition is, right? Now, what's an example of eddy current? So the best example of eddy current is what we saw last class with the motor. So what happens in a motor is that you provide current, and as the current passes through the motor, what happens is based on Fleming's left-hand rule, what is generated? Force, right? And because of that force, this thing starts to spin very fast. And as it's spinning, it's cutting the magnetic field lines as well. And as it cuts the magnetic field lines, we know that based on Faraday's law, if you happen to cut field lines, what's induced in it? EMF, right? And it's a conductor, which means that what will start to flow here? Current. But unfortunately, there's something called the Lenz's law, which states that whatever happens, we'll try to oppose it. So this is the motion that you are investing current to generate. But the Lenz's law will produce a current to what that motion opposite, right? So is it something beneficial or is it something detrimental or causing like loss for you? Right. So whenever it's a loss, it's called an eddy current. So in a generator, the current that's eddy current is what we actually use. So we don't call it eddy current because it's actually what we want, right? But in this case, we didn't want that. We wanted what rather? We wanted the motion and the current reduced to the motion, right? So that's why it's called an eddy current. Now, there's some very interesting uses of eddy current. This is one of them. So it's called regenerative braking. Does anyone know what's regenerative braking? Regenerative braking. Can you explain?
It takes at least for cars, it takes moving cars, energy, produces, I guess, charge for an EV.
Right, and recharges the battery. So I'll explain what regenerative braking is. So it uses eddy current, okay? So regenerative braking is this idea, it came in the 70s. So when your car is moving very fast, the tire is spinning very fast, right? So somebody came up with an idea, it's spinning. And then what are you using to spin the tire? Petrol, right? Combustion engine, internal combustion engine. So tire don't spin core. So somebody thought, let's put some magnets there. And if you put some magnets there, right, wouldn't the spinning of the tire cut the field lines and produce electricity? And wouldn't you use that electricity for something in the car? And eventually we did that. Gaari je engine ka belt thake, combustion engine that rotates and produces electricity. And we use that electricity for what? Everything in the car, your radio, your AC, your headlights, everything comes from there. So that's why you have to start the engine to, get those running. Normally, you can just get the lights on. But AC, you need to start the car because that's where the energy comes from, right? So we have been using this. It's called a dynamo. It produces electricity, right? But then somebody thought, let's put them next to the tire, like big magnets, and let's cut the field lines. And surprisingly, what they found is that if you take these big magnets and place them next to the rotating disc here, right? This is the tire, by the way. We find that as your car is spinning, I'll show you another version of this. So let's think of a normal tire in your car. So how does a typical braking system work? Ki hoy ekta normal car brake system Okay, look at this. This is your car tire. You're looking at the car tire from the front. This is the front view. And your car tire is spinning. How does normal brakes work? When a normal gari brake can be clutch for it. So they're called discs and pads. So when a tire is spinning, right, there are these brake pads, they press on the tire and they generate what? Friction. And that car braking, right, all that kinetic energy, it's insane amounts of K. If you just do a simple math, your car going at 100 kilometers per hour, right, it's almost 500,000 joules of K. Where does that go when a car brakes? Heat, just pure heat, and it's wasted. Now it heats up so much that we have to use like ceramics and different kinds of material in our brake pads so that they don't overheat. Because if you use materials that are not heat resistant, right, they'll melt. In fact, like Formula One cars, the heat is so much, even these things glow red. Ato heat generate by. There's insane amounts of K is lost in a very short time, right? So yeah, there's a lot of energy to be used. But the problem is with typical brake system, the energy is lost as heat. Now somebody thought, how about we put some magnets here? Ki hoy dekhi. So they put a magnet here and they put a magnet there. And this is with your normal brakes, by the way. And they put a disc inside the tire. Like there's a disc inside the tire that is connected to a battery, but what a portable to see. So there's a disc here. And as the car is spinning, the tire is spinning, and you bring the brakes in, right? What happens is there's a magnetic field line generated between the two magnets. And the spinning tire, what those field lines? Cuts them, right? They're perfectly cut here. See, so as this spins, right, the magnetic field lines have been cut here. And as magnetic field lines have been cut, can you tell me what is induced here? If magnetic field lines have been cut, what is induced in this disk? EMF, right? Now suddenly we can take the kinetic energy of our object, right? So this is kinetic energy of your car, and we can convert that to what? Electrical energy, okay? Because you have EMF induced. Or they took the disk here and they connected to a battery. So every time your car stops, right, what are you doing to the battery? You're charging it, right? So that's why it's called regenerative braking. The term regenerative means that you're regenerating energy. Typically, it's entirely lost. You're taking that energy and you're storing that in a battery. Now, it took a very long time for us to come up with this. The concept was there since 60s. The problem was that cars don't have a rechargeable battery. Your typical car just has like a lead acid battery. But once we came with hybrid cars where there's a battery out there and it's rechargeable, this became like a game changer. Why? Every time your car brakes, up to 30% of the energy that the car has is given back again. And in some cases, even more, because the idea is the faster you go, the more it charges. Obviously, the faster you go, the better the cutting rate, right? But then it's a brake can bola hoy, regenerative braking. So there's an interest in physics behind this. When you're bringing the magnets in, aren't the magnetic field lines been cut by the disk here? What is induced because of that? EMF, right? And then what's generated? And that current produces a magnetic field to what the motion, right? And that Lenz's law stops your car. So the regenerative braking is that the Lenz's law is actually slowing your car down. But there's a catch there. These brakes are very bad. There's a limitation here. Do you know why? Because these brakes will only work well when you're moving fast. Because if you move fast, you cut the field lines more, you produce more EMF, you produce more current, and then more current produces more what effect? Slowing effect. Egla jokhon slow speed e jao, these brakes are very sticky. Because they're not good on their own. That's why cars still need to have what brakes? Mechanical brakes. The mechanical brakes are for slow speeds. For high speeds, we use the regenerative braking. Okay, so yeah, this is the thing. Now the current that's generated here is usually considered to be eddy current if you don't recharge it. But if you recharge it, it becomes what? Something that you want, right? So then we don't call it eddy current. Okay. So yeah, this is the example of eddy current. If anyone's wondering, we are doing a discussion of the whole chapter. We are done with the chapter. So tomorrow kono question thakle bolo. Aজকে আমি transformers গুলো দেখাবো. But তাছাড়া, if you have anything else for me to recap from last class, বলতে পারো. So we're looking at ideas of Lenz's law. Okay, I've uploaded these things. These are in Google Classroom. If you check them, সবই আছে. So, কোনো question? এই chapter থেকে almost guaranteed one question. Maybe two. Okay, কোন chapter? Force on a conductor, force on a charge, and induction. I think they definitely একটা তো আসবে দুইটাও দেয় মাঝে মাঝে, especially the question would be from here, and there's something called the Hall probe. Hall probe, do you remember Hall probe? What was the formula for Hall voltage? BI divided by NTU. Okay, so that's this one. It recent papers both are very popular. I'm giving you heads up because some of you might have your exams coming up, so exams preparation is এটা যেমন হচ্ছে must. This one. Okay, it's definitely there. Okay, let's look into the transformer. So কারো কোনো question থাকলে আমাকে বলতে পারো before I start the transformer in your exam. How many equations are there? Let's do a recap. Phi equals to B into A, F equals to BIL, then BQV, then you have EMF equals to minus N d phi by dt, then Hall voltage equals to BI divided by NTQ, then there's this velocity selector V divided by BD, right? And there are some fringe equations. For example, we have the R equals to BQ divided by R equals to MV divided by BQ, the radius of a charge in a magnetic field. This one, the one I said that will make you derive every year. This centripetal force equals to magnetic force. Okay, if you get a question from this topic, this is it. This is what will make you answer it. Okay, এখান থেকে তো আসছে যে BQV থেকে আর কিছু রকম নাই equation wise. And laws, there are 5 definitions, very important definition. Number 1 is what's the definition of magnetic field strength. So we use which equation to define this? BI. Yeah. So F equals to BIL, B equals to F divided by IL. So magnetic field strength is the amount of strength of a magnet when a force of 1 Newton acts on a unit length wire carrying a unit ampere current. Okay, we don't say it's the amount of magnetic flux per unit area. Okay, that's the more literal version of it, but the definition is a little different. Okay, you have Lenz's law, Faraday's law. These are like the main definitions. For this one or the previous one? This one, right? So as you take your conductor from this edge and you move it through the magnetic field and you come out from that side, the phi variation is going to be like this. Why? Because right at the edge, the phi is almost 0. And as you start to enter the magnet, right, like the magnetic field, you'll find that the strength keeps increasing, and it increases randomly. Generally, we decided to increase it this way. It could be that way. It could be that way. It depends from magnet to magnet. Okay. Once you enter, it's a very uniform magnetic field. So as a result, you have a constant magnetic flux here. And then as you leave it, it leaves the same way. So that's the variation of your what? Phi with distance. Now we understand that if you move through a magnetic field and you cut field lines, right, what is induced? EMF, right? So that means the rate at which this thing is changing will give me my EMF. But there was a catch here. The catch was you're moving at what speed? Constant speed, right? So if you move at a constant speed through this field, you'll find that at the center, you won't have any EMF induced. Why? Because if you're moving at a constant rate, the rate of change of flux is 0 because it's phi. So the change is not there. So at constant speed, you'll find that this is 0. So the easy way of remembering what to have, derive from the upper graph is to just differentiate it. So if you differentiate this graph, whatever the answer, that's the answer. Okay. So differentiation of a curve is a straight line, differentiation of a flat line is a 0, right? So using that, you can come up with the answer. And as we saw, they actually do give this in the exam quite often. This is like the last, it's like very long back, but recent papers still power. The skill you need to have here is to know how to visually differentiate, not equation, just by looking at the graph. This one. Yeah, okay. So this one is essentially. So what's happening here is that you drop a magnet to a coil, right? So as the magnet drops to the coil, obviously EMF will be induced. So we use a CRO here to see how does the EMF vary. And then the graph looks like this. So while entering, there's like a small peak, and then it's flat for a the entirety it's inside. And then when it comes out, there's a very sharp peak like that. So the question is that why are the peaks here? Why are they opposite? Why are they of different magnitude? Why is it 0 at the center? It's like a 5-mark question, right? So first of all, why do we have a peak here? Because as the magnet enters, the magnetic field lines have been cut by the coil, but only which field has been cut right now? North. So there's like an EMF induced. And that EMF becomes greater and greater the closer you get, because what's increasing? The strength of your magnet. Once you enter the coil, right, something interesting happens. As you enter the coil, the north has been cut on this side, the south has been cut on that side. EMF is induced, a current is generated, But turns out, because of Lenz's law, as the north tries to move this way to oppose the motion, what do you have here? A north pole. But as the south is trying to move away and you want to oppose that, what do you have here? A north pole. So because there are two north poles on either sides of the coil, it means that they're trying to push the electrons in opposite direction. As a consequence, what will your net flow be? 0, right? So that's the reason why at the center we find that there's actually no net EMF. No net EMF. There's actually EMF, but it gets cancelled out. Okay, it's like connecting two oppositely poled batteries in a circuit, right? Also, very important that the area under the graph gives you the phi. So this area and that area must be same. Now, as it falls, it's slightly faster than as it entered, because it's still accelerating, right? So if the rate of cutting is higher, what would your EMF be? Greater, right? But previously north was been cut, now south has been cut. So EMF would be same polarity or opposite? Yeah, that's so you have an opposite higher polarity here. Right, so transformers. Transformers is basically like segue to the next topic on the AC currents. Asha, I just want to do a quick recap of your O levels. Who can answer why we need transformers? Right. Why do you want to do that? Only thing on so yeah, that's the reason. Okay, so when we want to transfer power through wires, right, we found that there's an issue. And I'll take you back to your O levels for this. O levels that are details at the A levels actually detailed to 9. So first of all, why do we need a transformer, right? So let me show you the diagram here. So if you think of transformer cam darker, so you have this power station, right? And this power station is producing electricity, and it's producing 400,000 watts of electricity. Okay, and you want to transfer this through what? Wires. As you transfer through wires, obviously wires will have what in them as you're transferring? Current. And we understand that whenever there's current in anything, okay, literally anything, what does the thing do? Heat up. Cannot. Why is heating like an effect that is associated with flow of current? Resistance, yes, but why would resistance cause heating? You're right, but what's the physics behind it? Yes, so resistance means that there are other particles in your path, and your electron is carrying the energy and moving, and those particles will what the movement? Hinder the movement. And every time they collide with those particles, what do? Transfer some energy, right? As a result, you're losing energy, and the object is gaining energy. So the object start heat up. So very good conductors, right, will not actually heat up that easily, because the current is actually not passing through the lattice ions. It's passing through this highway around it. It's called the what? Delocalized electrons, right? So, metals will not heat up as quickly as, let's say, a non-metal or something that's very high resistance. So yeah, point is, current thakle heat up kore. And this is the formula for the heating process, I square R. And our current is 50 ampere, our resistance is 100 ohms. 100 ohms ki pura jinishta 100 ohms, okay? the total power loss is 250,000. So if you look at the bigger picture, you have 400,000 generated and 250,000 wasted, right? What is the efficiency of your system? Just 37.5, which is, this is a business, right? A business, that's not a good outcome. When you are expending a coal, setting up a power station, you're producing electricity. People won't buy for what you produce. People will buy for what they use. They're gonna pay for what the amount they're using. You can't tell them, "Na, amar tonik loss pay me more," right? They wouldn't do that. Now you can increase the price, right? So why am I saying this? What's the motive in reducing this? It's a financial thing at the end of the day. Okay. Now, what did we do? So we figured out this equation is our problem. I square R. This is the loss. And there are two ways I can reduce the loss, either by reducing the what? Resistance, or by reducing the current. Now, reducing resistance is actually a viable solution, but we are using copper. And copper, if you want to go to something better in terms of conductivity, it's gold, right? And the resistance value will not change much. It'll go from 100 to 80. Now, the change is very minimal. So, that investment of having gold, transmission wires, right, will barely give you any return. In fact, this company will go bankrupt, right? Profit. So they found only if there was a magical way that we can reduce current. And, first thing students will say, increase resistance, right? Resistance current. But then again, you're increasing resistance. What are you doing again? Power loss part to say. So the hypothetical thing that we came up with was that if only there was a way that I can keep my watt same power, and I could increase the voltage that I'm transmitting so that current becomes what? Less. That was the ideal scenario. And then eventually after, I think if you remember this experiment, we figured out there's actually a way. It's this device called a transformer. So transformer only purpose is to step up or step down the voltage based on your need. Okay, so step up, step down transformer, and then we design the transformer. So this is called an ideal transformer. Okay, so like if you're very lucky, you'll get this in your A2. I mean, it has come before. So when I do the Asha, it's just the same cut and paste 5-mark answer, right? Before I answer, I want to see how far you remember. So, where does it all start? Primary coil, right? Very good. And the primary coil has what supply? AC supply. And the AC supply passes through this coil here. And the AC supply produces a what around the coil? Magnetic field. But because it's an alternating magnetic field or alternating current, the magnetic field also what? Alternates, right? It keeps changing direction. But this magnetic field has to go from here to where? Secondary coil. And who helps achieve that? Iron core. So iron core because the magnetic field is and because it's alternating, it's going back and forth like that. As it keeps going back and forth like that, the field line gets what by this coil? Cut by the coil. And because of that, what is induced here? EMF. But this is where the trick is. If there are 10 turns here and there are 10 turns there, whatever flux is generated will be whatever flux is cut. But if there are 10 turns here and 200 turns here, for every flux out there, it's getting cut more number of times. And it's not 1:1. Just imagine one coil producing a flux cut by one coil. It's a 1:1 cutting. But if one produces a flux and 3 of them cuts there, EMF can be 3 times because 3 of them are producing EMF across them, right? So if we can increase the number of turns here, then the voltage ki hobe. EMF. But there's no free voltage out there. So what's the catch here? Current because our power ki thakte hobe. Same. This is very important. A transformer, at the end of the day, is a what transferring device? Power transferring device, right? So you can take in a power the same voltage current and I then transmit it. This is all O levels. So A level second way. So A level part to explain so Lenz's law. It has to make a entry somewhere, right? So how is Lenz's law playing a role here? So it turns out as the EMF is induced here, magnetic field lines are going through the core like that, back and forth. And as the magnetic field lines go through the core back and forth like that, not that we wanted, but the iron core also what the magnetic field line cuts it. The iron core field line we were only using the iron core for what purpose? transmission purpose, right? But this happens to cut it because it's a conductor, right? And it's a metal and everything. As it cuts the magnetic field lines, what's induced in that iron core as well? EMF. And if it's like a complete loop here, what will start to flow here? Current, right? And that current is something we don't want. It causes loss. That's why it's called a what current. Yeah, this is the best example of eddy current. That's why you can almost 20 to 30% loss because the core heats up. So over the years, we wanted to make this better. So we came up with some modifications. Number one modification, heat. Gap, right? So I made a gap here, I made a gap here. How it's not going to be 100% efficient. There's still going to be current generated. How can I reduce that? Right. So no. I guess start with act a gap is not enough, right? So just a corora is this. This is actually how the core of a transformer looks like. It's made up of thousands of very thin sheets known as laminations. Laminations such a paper model. And every paper and every sheet is separated, right? So when current tries to flow through them, they're restricted to one place. And because they're restricted to one place, right, current beshi hoy na. So students will argue that why is this not good enough? Because current can flow like this, it'll make its own small loops everywhere, and current will still flow. So I want to restrict it everywhere. So where do I need to cut? Everywhere, okay? And this is called laminations. A lamination, the main purpose is to reduce the eddy current out there. On top of that, modifications, for example, this whole thing is in this oil that insulates it and prevents like heating up, right? Feature we are looking for the magnetic part of it, okay? So yeah, that is the transformer. I'll show you some animations of the working. Question to it just eddy current okay? And then there's something else I'll be showing you right now. Try so transformer. Right. So, I mean, it's kind of obvious. You have your AC supply on the left-hand side, and you have your bulb on the right-hand side. And just monitor that the coil is not connected to the core. Okay. So, clearly, but I'll try. So, you see it's not attached to the core. There's actually a gap. It's wound around the core, not on the core. Why? Yes, because if the wiring was on the iron, right, the iron would become part of the circuit. And instead of transferring magnetic field, what would directly just pass? Current. And then it's pointless, right? So we just want to make sure that the iron is there to effectively transfer the what? Magnetic field from the primary to the secondary. Okay? Iron core cut no problem. No. It's actually good for us. We don't want current to go that place. We want what to pass through? Magnetic field. And yes, magnetic field can pass through gaps. So it's not a problem. Okay, I don't need a complete circuit out there. So yeah, this is your transformer. A level se ki chahe ora? So A level se eddy current ta chahe, but there's an additional thing that you need to learn. Oita boli. তোমরা হচ্ছে আমাকে explain করবা the input and output of a transformer. Let me show you here. So yeah, this is the answer. The working one, discuss everything that we mentioned is here right now. But I want you to try something, which is আমার হচ্ছে a transformer primary coilটা এটা দেখতে. I'll show you what this is, and you need to tell me what the secondary coil output is supposed to look like. So primary coil, we have current produced, and the current is alternating, so it produces a shape that looks like this. You need to tell me secondary coil je current ta pabo amra, right, or je EMF ta induce hobe, what does that look like? So tell me the graph you expect for the EMF induced in the secondary coil. Let's assume yes, same turn, which is not a good transformer, but if it helps. So ki hobe? Tell me what the shape of the output is going to be. Eta hocche 1, 2, 3, 4, 5 marks. Yes. So exam আর to help করে আমি help করবো না which is like they'll break it down for you আচ্ছা so I want you to directly tell me if my input is this blue wave here how does the output look like so to give you more context our input touches in the primary coil things happen there's an output in the secondary coil if I observe the input and output and compare how do they compare I mean it could be the same it could be different it could be very different so figure out
So how many waves are there?
let's say 10-10 yeah like it's a 1:1 transformer so the y-axis value is not the concern we're looking for the shape like this
Yes, the reverse.
on the reverse how did you come up with that
I is equal to 5.
change in I is change in phi yes তারপর
Then change in EMF.
so you're telling me differentiation of this graph is a triangle grade 9 trigonometry additional math you have a sine curve you differentiate that what do you get a triangle eh? minus sign what's the differentiation of sign right well my question is very straightforward you're like negative cosine graph negative cosine why negative cosine acha okay anyone else any other shape ki kono kichu na negative cosine acha okay আমি explain করি it's the answer okay I'm do that okay so কি করতে হয় there are steps in between okay I know I've given it in such a way there's like a lot of question mark here but how do you get from here to there right so first of all this is your current graph current যেভাবে vary করে exactly same ভাবে কি vary করবে like current determines the variation of what first step phi magnetic flux because current first generates magnetic flux so the magnetic flux graph here is going to look exactly the same as the current always remember that it's free one mark okay but then to get from the magnetic flux to EMF you need to differentiate what the phi graph মানে যে আমি মাঝখানে কানেকশন গুলো দিয়ে দিব but if you differentiate this you'll get this right which is going to be my EMF graph so this is d phi by dt graph can you tell me what is d phi by dt going to be here like what's the differentiation of this curve it's a sine curve so if you differentiate cosine right so এটা cosine হবে which একটা জিনিস করব আমি এখন তোমরা একটু দেখো রিকল করতে পারো নাকি a cosine function is a what of a sine function other than differentiation yes how much yes it's a 90-degree phase shift আচ্ছা do you know that sine and cosine is shifted by 90 degree so এটা পাস পেপারে জিজ্ঞেস করে ওরা জিজ্ঞেস করে যে তোমার ইনপুট এন্ড আউটপুটের ফেজ ডিফারেন্স কত so what is it 90 আচ্ছা but not yet because আমরা জাস্ট এটাকে এটা থেকে ডিফারেন্সিয়েট করলাম but EMF is not the differentiation of phi only what is there as well negative because of what Lenz's law so your outcome is actually going to be what of this graph reverse achha so the outcome is going to be this and what would you call this graph negative cosine right so that's the answer so which means your graph has shifted how much here 90 degrees because actually it's our original graph chilo na isn't this now shifted forwards 90 degrees right so the input and output of a transformer is not the same it's actually shifted by 90 degrees okay so there's a question like that তোমাদের review question রাখছি আমি এটা but this is the process so how do you get from there to there what are the steps so step number 1 হচ্ছে if you want to go from here to there same কেন I and phi are what directly proportional okay Then from here to there, how do you go? From here to there. d phi by dt is proportional to my EMF, but it's not equal to my EMF. And then from here to there, we do what? Minus d phi by dt is actually equal to what? EMF. And then minus sign that we place there is acknowledged in what law? Lenz's law. So, if you're lucky, they'll give you this graph. They can give you some random graph and not expect the whole process as well, okay? This question. এটা ছিল হচ্ছে the easy one. Current দিছে, phi দিছে, EMF দিছে. So এটা sine হবে, minus cosine হবে, okay? I think it's ওই যে last কি বলছে, what is the phase difference here? 90 degree, okay? আর যদি ওরা চ্যালেঞ্জিং করতে চায় তাহলে যে এটা করবে. This. So apparently input current এরকম ছিল for whatever reason, and since the input current is like this, output 3 marks এর জন্য, so directly output draw করতে হবে. Right, so that is the transform part that was pending. এটা আমরা আরো ডিটেইলসে করব, কোথায় করব বলে দিচ্ছি। আমাদের next chapter is called AC currents. So AC currents will go in depth with this. But I think এখানে হচ্ছে মনে রাখাটা or discuss করাটা better. So তোমরা একটু পড়ে দেখো if you have any questions. Any question? Talk about the borough. There are a few questions here for revision purpose. I have to answer. So it's basically one mark MCQs from the entire syllabus from random places. Okay, what is motor effect? It's a quick summary. It's just I don't just refresh your memory. So what's motor effect? Again, we are summarizing the whole chapter here. Motor effect কোনটা? Cutting হয়? Yeah, so option 2 দেখো, options দেখতে পারো না? আচ্ছা, তোমরা দেখতে পারছো না, sorry. There are options on screen. That right. That's the option. The force exerted when magnetic fields of magnet and current conductor interact, the rotation of an electric motor, the generation of current in a wire, the creation of magnetic field. Which one is motor effect? B. The rotation of an electric motor is not motor effect. That's a motor. So it uses the thing, right? So A, right? Correct. What happens to the energy in an underdamped oscillation? Yes, underdamped, by the way, is known as also what damping? Light damping. Over time, gradually. So first, the energy remains constant. Undamped, right? Energy is gained over time. Force oscillation, because it is energy is lost immediately. Almost immediately after critical damping, okay? But it is over time, right? What is the main assumption about gas particles in an ideal gas equation? Particles have different sizes. They move in a straight line only. Particles have significant volume compared to the container. particles undergo random zigzag motion? D. Yes. It's called Brownian motion. Achha. Why is half the energy lost when charging a capacitor? Remember the graph? QV, half QV, why? Yeah, due to overcome an electron repulsion from the capacitor. Okay. What happens during simple harmonic motion? Yeah, A is directly proportional to minus X, right? Or what's the formula? A equals to minus omega square X. What is the relationship between gravitational field lines and field strength? What's the link between the lines and the strength? C, correct. What happens to internal energy during state change? Yeah, okay. What happens to internal energy during state change? B. That's because আমার হচ্ছে K টা বাড়ে না, but potential energy বাড়ে. Always remember, whenever you're providing heat, internal বাড়তেই থাকবে. K আর potential এর মধ্যে change হতে থাকে. What is electric field strength? Yeah. তারপর হচ্ছে, how can the strength of a solenoid be increased? See, right. What is temperature a measure of? Yeah, very good. We'll do more. This is unlimited. So the whole documentary উপরে যতগুলো কিছু তোমাদেরকে বুঝাইছি, you can take question আসে. So I'll be doing this more often. এই বইটা শেষ হয়ে গেছে তো, so just to refresh everything. Random. I don't know কি জিজ্ঞেস করবে ওরা. So what is gravitational potential? The amount of work done needed to move a unit point mass from infinity to a point in that gravitational field, right? It's phi equals to minus, right? Why are gravitational potential values always negative near mass? Good question. Yes. Okay. What is thermal equilibrium? Yes. What is time constant of capacitor? Yeah, it's the time taken for a capacitors, whatever the quantity to become 1 by E, the initial value, right? What happens during resonance? Yeah, the natural frequency and force frequency become equal, resulting in increased amplitude. What is internal energy? Sum of random kinetic energy and the potential energy of the particles. Why is the equation Gp equals to mgh not valid for large distances? Yeah, right. What is specific capacity? Is the energy needed to raise the temperature of 1 kg substance by 1 degree Celsius or 1 Kelvin, right? What is the main characteristic of a geostationary satellite? Yeah. And why does pressure increase when volume decreases in a container? Yeah. Right. So next class I'll be starting AC currents, but I think you should definitely communicate because ওইখানে যেতে আমার time লাগবে, so this is your bridge rectifier. You know what a bridge rectifier is? Bridge rectifier? No. Data? So do you have it in your exams? Bridge rectifier? AC currents. It is in AC currents. It is AC currents. Full wave rectification. That's the name of the process, but the device name is called the bridge rectifier. Bridge rectifier টা একটা আছে, আর একটা হচ্ছে smoothing. আচ্ছা, anyways, আমি bridge rectifier একটু বুঝাই। এটা O levels এর ছিল, তো I think তোমরা পারবা। মানে তোমাদের ছিল না, it used to be in O levels before, they got rid of it. So what is a bridge rectifier? So bridge rectifier problemটা হচ্ছে যেটা solve করে, it's actually quite useful. Look at this. You have an AC supply here and you have like a component, and I connect my CRO across the component to see what the output is. So AC, if you don't know, is actually a sine function or a sinusoidal function. So the light that you see here right now is actually a sine graph. And then if it's a sine graph, what's the evidence it's a sine graph? So you'll find that whenever it's a sine function, there are moments here when what is the value for your current or voltage? Zero, right? Which technically means that the lamps here, they must be turning on and off, right? Are they? Yes, absolutely they are. It's just that you're not capable to see it. That's your problem. So if you're a cat, and it'll be actually a problem for you. Because it's like, I don't know, how do they survive in lamps? But it's like our eyes can pick up certain movements. Human eyes are very lazy. So that, we don't see it, it blurs it out, right? So I'll show you which one? TV. No, it is যেকোনো ল্যাম্পই হয়। এটাতে হবে না, because this is an LED. Why doesn't it happen with LEDs? LED works on DC supply. It's a diode, right? তার জন্য fix করতে হয়। But if I point it at, I don't দেখতে পারবো। Do you see flicker? এই যে দেখা যাচ্ছে না? I mean, you're not supposed to see anything, just flicker to দেখবা। flicker হচ্ছে, right? So this flicker that you're seeing right now is actually happening. So the lamp is turning on and off right now, this moment. So if I had like a very high frame rate slow motion camera, I would see the lamp go on and off and on and off multiple times every second, right? But luckily our eyes have this mechanism where this very rapid movement, it blurs it out. So we can't see it. Why? Because it's very fast for us. But yeah, it is happening. But appliances suffer from it. So আমাদের দরকার হচ্ছে appliance গুলোকে rectify করা, like convert the AC to DC. So the first step in that is to place a what here? Diode. And once you place a diode here, can you tell me what would the output look like? Yeah, that, right? So that's fine. I mean, it did do its job, but you just wasted half the energy. Right? Just half the energy has disappeared. You're still paying for it, but use it, right? So that's when they decided that, is there a way we could do this? Like bring it back to the top. So they came up with this circuit. It's called a bridge rectifier. Okay, it's very simple to understand. So you take your component and you place it between 2 points A and B, and observe the direction of current flow between A and B. Okay, so let's start from here. Current edike jabe. As it goes there are two options. Where does it go? Left, because that's called forward bias. It comes here, there are two options, straight or down. Which way? Straight. And it enters from where? A, and leaves from where? B, and it comes to that junction there. Now there are two options, up and down. Where will it go? Why? Yes, because your current can't flow back to plus. So it'll always seek out which part? Minus. Imagine this is a pipe and water flowing. Does the water flow back up the pipe? No, right? Where does the water keep flowing? Down, right? So it'll come here. Does the water flow back up the pipe? No, so it'll go this way and then it'll go to the negative terminal. So which way did the current flow here? From A to B. আমরা এখন কি করব? Reverse cycle use করব। মানে এটাকে প্লাস করে দিব, এটাকে মাইনাস করে দিব, যে নিচে উল্টাটা, right? Let's follow the current. So the current goes this way, the current comes here. Which way does it go? Left. Which way does it go? Yeah, it can't go up, it'll go right. And once again, where does it enter? And leaves where? B, right? And makes its way out like that. So if you add the resistor, every single cycle, you'll find the current entering from which side? A, and leaving from which side? B, right? So eventually, this is how it looks like. It's called a full wave rectification. But we are not happy with that though, because what is it doing right now? Fluctuating, right? We want to make it what? Flat. Check them flat. So there's a much more elaborate process. যেটা আমরা পরে শিখবো, আচ্ছা? So that eventually you can just make it flat like that. So that's called the smoothing, where you can make an AC supply into a perfect watt supply. DC, okay, like constant DC.